Hi everyone, welcome to our video where we're going to do partial derivative problems and then evaluate them at given values. Alright, so for this first one, we have a log function. Let's break this down. So I'm going to do my blue with the partial derivative of f with respect to x. Alright, so I've got a log function here. Well, the way that I usually do log functions, and I'm going to keep it the same way, let's just jump right into it. So my partial derivative of f with respect to x. Now, a log function derivative in words is to put the whole argument down below. So 4 plus 2x squared y to the fifth minus y, just like that. And then times the top, or write the top as the derivative of this denominator, but we just have to make sure with respect to x. All right, so the derivative of 4 would be 0. The derivative of, and I'll even put a placeholder for that, derivative of 4 is 0, and then we have plus 2. With respect to x, that means the derivative of x squared is 2x. Y to the fifth is just attached, it's just tagging along, it's treated like a constant, just like that front 2 was. And then the derivative of y is 0 because we're doing it with respect to x. So again, that's treated like a constant. The derivative of a constant is 0. And so now let's clean that up. So we have our partial derivative. So it looks like the numerator just becomes 2 times 2 is 4x y to the fifth over the same old denominator, 4 plus 2x squared y to the fifth minus y. All right, there we go. All right, so that's that portion, so we found it. Let's box it. And then now let's evaluate it. Well, when evaluating these problems, let me keep my color going. This is the x coordinate, okay, so just like it is right there. And then the second one would be the y coordinate. And so we're just going to plug that all in. So we have f little x negative 2 comma 0. So this is the partial derivative of f with respect to x equals. And then now I just have to make sure I change all of the x's into negative 2 in this equation right here. And then I need to change all the y's into 0. Okay, so it looks like I would have 4 times the x, which is negative 2, times the y, which is 0, to the fifth, over 4 plus 2 times negative 2 times 0 to the fifth minus 0. Okay, and then it looks like it simplifies pretty nicely up top there. So our partial derivative with respect to x at negative 2 comma 0 is, it looks like it's just 0 up top, over, and it looks like it's 4 down below, but that simplifies to be just 0. Okay, and what this will represent, we'll do an application in a different video, but it's just representing the rate of change of x, the rate of change of our function with respect to x, again, treating y as some constant. Okay, so it's still a rate of change, but with respect to x in this scenario. Okay, and then let's do green again for our second portion. Okay, so now I want to do the derivative with respect to y. Well, I'm going to set it up the same way, or a very similar way, where we know the derivative of a log function is to take the whole argument in there and put it down at the denominator again. So still 4 plus 2x squared y to the fifth minus y getting thrown down there. And then in the numerator is the derivative of this with respect to y. So the derivative of 4 is still 0. And then we have plus 2x squared. So x is like a constant, so we just attach it. So the 2x squared, there we go. So 2x squared is just tagging along. And then the derivative of y to the fifth would be 5y to the fourth. And then the derivative of minus y would be minus 1. Okay, so I just went through it term by term, and now we just need to simplify. So we have our partial derivative with respect to y is equal to, okay, so it looks like this would simplify to be 10x squared y to the 4 minus 1 over 4 plus 2x squared y to the fifth minus y. All right, that's it. Okay, and then now our second step is to do the evaluation. All right, so we have our partial derivative with respect to y at these coordinates, 5, negative 3, and we'll plug all of that in to the respective spots up there. So again, all the x's should be 5, all the y's should be -3. And when we do that, we'll have 10 times 5 squared times -3 to the 4th minus 1. And then 4 plus 2 times 5 squared times -3 to the 5th minus -3. Okay, so these numbers didn't simplify as nicely as that first one. Okay, so we still have, let me fix that. Okay, so now I'm just simplifying this. I think we'll need a calculator here to help us. Let me maybe not make that so long. Okay, so up top, it looks like we would have 5 squared is 25, -3 squared is 81. Yep, I can't do that mentally, so let's go to a scientific calculator. Okay, so I'm going to pull up our Desmos. There it is. Okay, and I'm just going to type that in where I have, let's all do it in one big one. So 10, 5 squared I can do. Let's just do 5 squared is 25 times -3 to the 4 would be 81. And then minus 1. And then it's all divided by 4 plus 2 times 5 squared. So still, let's just do that as 25. -3 to the 5th. Maybe let's do that one in parentheses. There we go. And then minus a -3, I could just do that as +3. There we go. And that's it. So does it change into a fraction? Oh, it does. Okay, so we have this as a decimal, though. And then that's its fraction. Might as well keep it as a fraction, because I already have that fraction written down there. Okay, so it was -20,000. 20,249 over 12,143. Which was approximately, let's go ahead and also write the decimal next to it, -1.668. There it is. Okay, we did it. Okay, which still, that represents a rate of change, but with respect to y instead of with respect to x. All right, and with those coordinates, whatever those represent in our scenario. All right, so there we go. Let's see one other in this video. So we've got an exponential function over this x squared minus y cubed. All right, well, let's see it. So we've got, let's do blue again for this one here. Okay, so to find our f with our partial derivative of f with respect to x, it looks like we've got, okay, so it looks like we've got a fraction. Well, it is a fraction, so we have e to the x over x squared minus y cubed. Now, it actually might be easier. Let me actually, so sorry I wrote that too soon. Let me rewrite that first part. So e to the x, it might be easier to see it, I don't know, like this. Okay, so I'm using the power rule. I'm not too sure which is better. Okay, so my bad. So this is an option. This is an option if you wanted to try to do that. That works just fine. It will eventually, but no, I'm gonna go back. I'm gonna rewrite it so I can mark things up. So f comma xy is equal to e to the x over x squared minus y cubed. All right, so here we've got a quotient where this has an x term in it. So this has an x term, and so does the bottom. So they both have x terms in it. So that means I'm doing an x divided by an x term, which means I need to do the quotient rule for this problem. Okay, so the quotient rule is involved. So I have this division. Okay, so if I'm doing an x term divided by an x term or an x term multiplied by an x term, I would have to do a quotient or product rule. Okay, and we haven't had that yet in any of these problems. We've only had x terms times y terms. So we haven't had both an x times an x or a y times a y. It's only been split xy. Okay, this time around, though, I have an x term divided by an x term, so that means I have to do the quotient rule. Okay, so now to do the quotient rule, well, I have my high D low and so forth. Okay, so let's set up our formula. So we've got low D high minus high D low all over low low. And then we'll plug all those in. Okay, so we have our partial derivative with respect to x is equal to, okay, so the low one is the x squared minus y cubed times the derivative of the high. Well, the derivative of the high is e to the x. It's with respect to x, that's it. Minus the high one, which is e to the x. Times the derivative of the low. Well, the derivative of the low with respect to x is 2x. And then that's it. The derivative of y cubed would be 0 because, again, it's with respect to x. And then all over the low one getting squared. So x squared minus y cubed squared. Okay, and then now we would just kind of clean this up. If there's anything to clean up, it looks like we could just factor out an e to the x. Okay, so let's go ahead and take that out. So we have our partial derivative with respect to x is equal to e to the x factored out, and then we're left with x squared minus y cubed minus 2x all over x squared minus y cubed squared. Okay, so the quotient rule still applied here. And then now what we need to do in the rest of this problem is, well, they just want us to evaluate something real quick. Oops, kind of blocked it all off. So now let's take care of that. Okay, so I just want to plug in 1 and 3 into all those x's and y's that we have in this equation. Oops, let me write actual 1 and 3. Okay, so our partial derivative with respect to x at 1, 3 is equal to e to the first, and then times x squared. Well, that's 1 getting squared. Oops, let me use parentheses. Looks like r. Okay, so 1 squared minus 3 cubed minus 2 times 1 over 1 squared minus 3 cubed, and then all of that's squared. Okay, and then in our numerator, I have an e, so I'm going to keep it in terms of e. I'm just going to put it at the end, though, so e to the first, I'm just writing as e. And then, but let's simplify what we have in this parenthesis. So 1 squared is 1, minus 27 would be negative 26, minus another 2 would be negative 24. So negative 24e. And then down below, let me go ahead and just use the calculator real quick on it. Okay, so 1 squared is 1, minus 3 cubed would be 27. Okay, so it's negative 26, but I need to square that. Okay, so let me do parentheses, negative 26 squared is 676. Okay, so we have 676 down below. And then let's see, I'm just going to see if that fraction reduces. It looks like it does. I mean, they're both even, so I know for sure it reduces a little. Oops. Okay, so I just want to do 24 divided by 676. Okay, so 6 over 169. So it's negative 6, negative 6e over 169 is a reduced fraction. So this is in terms of e in case they wanted it in terms of e. If you need a decimal, just multiply it out. Use e as the number, e, 2.71, so forth, and then from there you get your decimal. Okay, so that's our quotient rule. All right, let's see if the other one needs it. All right, so I want to do our partial derivative with respect to y. Well, our f of x, so with and this also had a y in it, but I was thinking only the partial derivative. So when we have our partial derivative, the e to the x over x squared minus y cubed, this is treated like a constant when we have our y, and then this is our y term. If you want to be safe, you could still do the quotient rule. Might as well. Let's do our quotient rule. So I've got my partial derivative with respect to y equals, okay, so I have my reference, my low one My low one is x squared minus y cubed. Okay, so there's the low. The derivative of the high, well, that's an x expression, so with respect to y, that would be 0. Minus, okay, so there's my low d high, minus my high one, which is e to the x, times the derivative of the low, which would be, okay, so the derivative of x squared is 0, because it's with respect to y. The derivative of negative y cubed would be negative 3y squared. And then all over the low one squared. There we go. Okay, so we notice the difference. And then now let's simplify where we've got our partial derivative is equal to, now the first term is just 0, so I don't need to write that. The second term, I have a negative and a negative, which would combine. So let's rewrite it as 3 y squared e to the x. Okay, so and I'm just rearranging it a little bit, so but that's all the terms, just mashed together. And then over x squared minus y cubed squared. Okay, so that is our partial derivative with respect to y. Okay, and then now one more thing. Let's just plug in our negative 2 and negative 4. So our partial derivative with respect to y, when we plug in negative 2 and negative 4. Again, all I want to do is just make sure I plug in the numbers into the correct spot. So any x I see, I need to plug in negative 2. So I have 3. And any y I see, I need negative 4. So I have 3 times negative 4 e to the negative 2 over x squared is, so negative 2 getting squared, minus y, which is negative 4 getting cubed, and then all of that would be squared. Okay, and then now it just looks like I need to simplify a little bit more. Up top, I'm going to squeeze it in right here, is negative 12 e to the negative 2. The denominator, I'm going to use my calculator again for help. Let's just plug that all in. Okay, so I have parentheses negative 2 getting squared, and then minus negative 4 in parentheses raised to the third, and then that's 68, and then so 68 will get squared, which gives us 4,624. And then, well, it looks like it simplifies again one more time here. Let's do that. And so I just want to do 12 divided by 4,624 and see what the fraction is. Okay, so that's as a fraction. So this is, again, if I wanted to keep it in terms of e. So I have 3e to the, I have negative. The negative's just hanging out still. So negative 3e to the negative 2. Okay, so it simplifies into negative 3e to the negative 2 over the 1,156. So that, and that's as a fraction. Again, if it wants a decimal, we could plug it in one more time and get a decimal. But I'm gonna leave it like that, just in case they wanted it in terms of e. Okay, so that's it. So notice our quotient rule. So on this, we used it well. I guess if you're ever unsure, just go ahead. If you see division, you could always do the quotient rule. Okay, but the main thing is they really only have to be used. Quotient rule or product rule only have to be used if we're doing the partial derivative and you have some, like with our partial derivative of x, if you have x term times another x term, or x term divided by another x term is when we would use them. With y, it would be a y term divided by a y term, or a y term times a y term is when we would use them. Okay, but I think either way it's going to be kind of tricky early on. Okay, so just get good practice in, and if you do have questions, let me know. Okay, but that's it for now. Thanks for watching, and I'll see you again soon.